You are welcome. Our discussion today is on moving charges in a magnetic field. So we are looking at what happens to a moving charge in a magnetic field, how the force in the field affects the movement and direction of the charge, and how the charges interact in the field. So moving charges in a magnetic field experience a magnetic force. So when the charges move parallel to the magnetic field, the force acting on the particle is zero. So when the charge is moving parallel to the magnetic field, the force acting on the particle is zero. When the particle's velocity makes an angle with the magnetic field, the magnetic force is in a direction perpendicular to both the velocity and the magnetic field. So from the right-hand rule, as we saw earlier, we know that the magnetic force equals charge times velocity times the magnetic field times sine theta. So when the magnetic field and the velocity is parallel, that is when theta is equal to 0 or 180 degrees, then the sine of 0 is 0, making the force 0. When the velocity is making an angle which is greater than 0 and less than 180, then the force has a value greater than 0. The force has a value greater than 0. That is, there will be a force when the velocity is making an angle to the magnetic field, and when the angle is greater than 0 and less than 180 degrees, there will be a force acting on the charge. Now, a magnetic force does no work on a moving charge particle because the magnetic force always acts in a direction that is perpendicular to the motion of the charge. So we know that work done is equal to force times distance, and the force that we are taking into consideration here is a force which is making an angle to the direction of the motion of the charge. So not the direct force is working on the charge, but a force at an angle is working on the charge. So therefore, the work done becomes F cos theta times the distance. The work done becomes F cos theta times the distance. So from the second equation, the charged particle experiences a force that moves the particle in a circular motion in the uniform field. So the charged particle experiences a force, and the force that is opposing on, or the force that's exerted on the charge, makes the particle move in a circular path. It makes the particle move in a circular path. So the force always remains perpendicular to the velocity, and the velocity is directed towards the center of the circular path. Since the magnetic force causes the charged particle to move in a circular path, centripetal force is then present to make the particle move along the circular path. So since we are talking about circular motion, centripetal force is present in the circular motion to keep the particle in its circular path. So the magnetic force initiates the circular motion of the particle, and the centripetal force keep the particle in its circular path. Now, the magnitude of the centripetal force depends on the velocity and the mass of the particle, as well as the radius of the circular path. So the velocity of the particle, the mass of the particle, and the radius of the circular path all contribute to the centripetal force present in the circular motion of the particle. So therefore, we know that centripetal force equals mass times velocity squared all over the radius. Centripetal force is equal to mass times velocity squared all over the radius. Now, since the magnetic force provides the centripetal force, they must always be equal to keep the particle in the circular path. Therefore, the magnetic force is equal to the centripetal force. So, equating these two relations, we have KOBB is equal to mv squared over r. KOBB is equal to mv squared over r. Now, this equation can be simplified. And a variable can be made the subject of this relation. So determining the radius of the circular path leaves the equation to be r equals mv over qb. So the radius of the circular path becomes mv over qb. So from this equation, we can see that the radius of the circular path is proportional to the momentum of the particle and inversely proportional to the charge and magnetic field. So the radius is proportional to the momentum, that is mass times velocity of the particle, and inversely proportional to the charge of the particle and the magnetic field present. So this equation is known as the cyclotron equation. It is used in the principle of mass spectrometer to identify particles. Now let's look at the mass spectrometer. So it is an instrument used for determining the relative masses and abundances of an isotope. It is used to determine the relative masses and abundances of isotopes, and it is an important tool in both chemistry and physics. Now, unknown chemicals can be heated and ionized, and the resulting particles are passed through the mass spectrometer and subsequently identified. So we can heat our chemicals, ionize it, and the particles are passed through a mass spectrometer to know out the specific chemical which was heated and ionized. So the mass spectrometer enables us to measure the mass to charge ratio by the magnetic principle. So using the magnetic principle, we can therefore measure the mass to charge ratio of a particle. We can measure the mass to charge ratio of a particle. So this is an outline of the mass spectrometer. So this is where the ion source is, or this is where the charge or the chemical particle is placed, and where it is ionized. It is heated and ionized and moved into the magnetic field, and therefore detected by the detector to know the type of particle we are dealing with. So atoms or molecules are vaporized and then ionized by the ion source, and the ions are then accelerated through the potential difference that is applied between the ion source and the metal plate. So from the diagram, the atoms or molecules are placed here, and they are vaporized and ionized. So after the ionization, they are accelerated through this path or through this metal slit by this potential difference. So when this potential difference is applied, they are accelerated through the slit to the magnetic field. So with a velocity, the ions pass through a hole in the plate and enter a region of constant magnetic field. So this is the hole I'm talking about, a metal slit. So a metal slit where the ionized particles will be passing through. So they pass through this hole, then they move to a region of constant magnetic field where they will be deflected into a semicircular path. So they are deflected into a semicircular path in the magnetic field. Only those ions following a circular path or following a path with proper radius strike the detector. So the ions following a path with proper radius strike the detector, which then records the number of ions arriving per second. So the ionated or the ionized particles which are in the magnetic field and following a regular or proper radius path in the field are detected, and the number of ions that are arriving per second are also detected by the detector in the spectrometer. Now, the magnetic force on the particle causes it to move in a circular trajectory of radius r. So therefore, the mass to charge ratio is given by m/q equals radius times the magnetic field over the velocity. So the m/q is the mass to charge ratio. So since this principle is used in the cyclotron, we then look at a cyclotron, which is a device for accelerating protons or other elementary particles. So a cyclotron tends to accelerate protons or other elementary particles. So the period of revolution of a cyclotron is therefore given by T equals 2 pi r over v. So we can therefore simplify the equation to make it 2 pi m over q times b. So therefore we know that frequency equals the inverse of period. Frequency is the inverse of period. So therefore, frequency will be equal to QB over 2 pi m. Frequency will be equal to QB over 2 pi m. So note that the frequency of the revolution is independent of the radius and velocity of the charge. The radius and velocity of the charge has no influence of the frequency of revolution. They have no influence of the frequency of the revolution. And this frequency is also termed as the cyclotron frequency. It is termed as the cyclotron frequency. Now let's look at the magnetic force on a current carrying conductor. That's a wire. So what is the force present in the wire that has moving charges and carrying current as well? So we have seen that a single charge moving through a magnetic field experiences a magnetic force, which is given by F equals QVB sine theta. So we've seen this equation earlier on. And since an electric current is a collection of moving charges, so moving charges present in a conductor brings out a current. So a current in a magnetic field can also experience a magnetic force. So we said that current is a collection of moving charges. So charges motion in the conductor brings out current. So therefore, a current in a field can experience a force. So the force is exerted on each moving charge in the wire. The force is exerted on each moving charge on the wire. So the collection of the moving charges brings out the current. So therefore, the force is exerted on each charge in the wire. And the total magnetic force on the wire is the sum of all the forces on the individual charges producing the current. So if we sum up all the forces which is exerted on the individual charges in the current carrying conductor, then we can get the total magnetic force on the wire. So now the force on the wire of length L is the net force acting on all the charges of total charges Q moving in the wire. So multiplying and dividing the right side of the equation by the time needed for the charges to travel the length of the wire. So in this equation, we take the right side of the equation, then we multiply part of it and divide part of it by t. Divide part of it by t, then multiply part of it by t. So we therefore divide Q by t, then multiply V by t, then keep the rest as they are. So we divide Q by t, then multiply V by t, then we keep the rest as they are. So the term QT or Q over T is current. So charge per unit time is current in the wire. And the term V times T is the length. That is velocity times time give distance. So the length of the wire is the velocity times the time. Therefore, doing these substitutions, we're having FB to be equal to current, which is Q over T, times length, which is V times T, times the magnetic field times sine theta. So our equation here for the current carrying conductor and the force acting on that conductor is I times L times B sine theta. So the magnetic force is maximum when the wire is oriented perpendicular to the field, and the force becomes zero when the wire is parallel or anti-parallel to the magnetic field. So we've seen that earlier. Now let's look at some work examples and know how these equations and these concepts are applied. So a charged particle enters a magnetic field of a mass spectrometer at a speed of 1.79 times 10 to the power 6 meter per second. It subsequently moves in a circular orbit with a radius of 16 centimeters in a uniform magnetic field of magnitude 0.350 Tesla, having a direction perpendicular to the particle's velocity. Find the particle's mass to charge ratio. Find the particle's mass to charge ratio. So now let's look at the solution to this problem. So in the equation, we have the speed at which the particle is moving the radius of the circular orbit of the particle, the magnetic field intensity, and the direction at which the field is to the particle's velocity. So now we write out the parameters that we have in the question: the velocity, the radius, the magnetic field, and the angle, which is 90. But here we don't need the angle. So the mass to charge ratio equation is m/k equals r times b over v. R times b over v. So we want the mass to charge ratio, which is m/k. Therefore, we do our substitutions. So we substitute our radius, which was 16 centimeters. So we convert it into meters. We convert 16 centimeters to meters, and we have 0.16 meters. Then we substitute the magnetic field, which is 0.350. Then the velocity, which is 1.79 times 10 to the power 6. So after substitution and computation, we're having mass to charge ratio to be 3.13 times 10 to the power minus 8 kilogram per coulomb. Kilogram per coulomb. So we use the standard unit for both mass and charge. So the mass to charge ratio for this particle is 3.13 times 10 to the power minus 8 kilogram per coulomb. Now let's look at another example. A cyclotron with a magnetic field of 1.5 Tesla is used to accelerate protons. If it has a d radius, r equals 0.5 meters, calculate the frequency, or calculate the cyclotron frequency. Calculate the cyclotron frequency. So into the solution of the problem, we state all the parameters given in the question. So we have the mass of proton, which is 1.6 times 10 to the power minus 27 kilogram. The radius, which is 0.5 meters. The magnetic field intensity, which is 1.5 Tesla. So we state out the frequency equation, cyclotron frequency, which is K times B over 2 pi m. K times B over 2 pi m. So our K is 1.6 times 10 to the power minus 19 coulomb. Then our B, which is 1.5. So we do all the necessary substitutions here. So we substitute our K, substitute our B, which is 1.5, 2 pi, which is a constant. Then our mass, which is 1.67 times 10 to the power minus 27. So after the substitution and computation, frequency here, the frequency here will be 23.8 times 10 to the power 6 Hz. 23.8 times 10 to the power 6 Hz. So this is the cyclotron frequency. This is the cyclotron frequency. Now there's a trial question here that you can work to get the solution of this problem.